What do you think of when you hear the word pod? Perhaps you think of a pea pod, or a dolphin pod, or an iPod. Well, now you can add a Kubernetes pod to that list. In Kubernetes, a pod holds one or more containers. These containers are always scheduled together, run on the same node, and share the same fate, meaning that when a pod dies, all of its containers die as well. Now, a pod is the smallest deployable component in Kubernetes. The direct implication is that you cannot deploy naked containers. Containers live inside of a pod, always. So, what is a pod, and what are its features? Let me try and explain. Every pod has its own unique cluster IP address. All of the containers inside that pod share the same IP address. They also share the pod's hostname, network interfaces, and ports. This means that the pod's containers must coordinate together to avoid using the same port. From a networking perspective, it's as if containers are all running on the same logical host. Every container has its own isolated file system. Containers cannot access files in other containers, but containers in the same pod can share storage using a Kubernetes volume. When a volume exists, it's attached to a pod. You'll learn all about this in the chapter on volumes. A pod's containers are always deployed together onto exactly one node. A pod's containers will never be split up and deployed onto different nodes. All pods in a Kubernetes cluster live in a flat network address space. This means that containers in one pod can communicate with containers in another pod without the help of network address translation. It's as if the pods are all computers which live on the same local area network. In other words, communication between pods is hassle-free, something that isn't always the case with other container orchestration solutions. All of the containers in a pod share the same IP address. They can communicate with each other via localhost or 127.0.0.1. They can also communicate with each other using IPC channels like pipes, Unix domain sockets, and so forth. This is another way in which containers in the same pod act like they're on the same logical host machine. Replication is the term used in the Kubernetes world to refer to horizontal scaling. This is where you run additional copies of the component which you want to scale out. For example, let's say that you manage an e-commerce website which is under considerable strain thanks to large holiday crowds. You know, one of those good news, bad news kind of situations. Anyway, you need to replicate your web server container to handle the heavy load. But here's the catch. You can't replicate containers directly in Kubernetes. In other words, you can't create additional containers in a pod. What Kubernetes does is replicate the pod. You see, when you create a new pod replica, Kubernetes automatically duplicates all of the containers in the pod. That's a pretty handy feature. Pods are ephemeral objects, i.e., they're not durable. This means that when a pod dies, it's dead and doesn't resurrect on its own. A pod can die or disappear for a number of reasons. Perhaps the node it's on fails. Or perhaps Kubernetes is in the process of scheduling the pod to a node and the scheduling operation fails. Pods can be convicted. You're guilty. Pods can be evicted when the node they're on runs out of resources. Pods can also be evicted when the node they're on undergoes maintenance. Pods don't have the ability to self-heal. That means that when a pod goes down, it stays down. The self-healing capability, which I touted to you at the beginning of this course, is actually provided by another kind of Kubernetes component called a controller. We'll go over those more later. Once you learn to use Kubernetes, you need to get a feel for designing clusters. One of the first skills that you need to master is the ability to determine when a container should be in its own pod or when multiple containers should live in a single pod. In this section, I'm going to try and convey to you some general principles for making these kinds of decisions. In general, most pods will only have one container. Now, you might be worried that this is inefficient, but it's not. Pods are lightweight, so don't try and stuff them full of containers in the name of efficiency. When should you put multiple containers in a single pod? Well, put multiple containers in the same pod if those containers are tightly coupled. Determining if two containers are tightly coupled is a bit of a judgment call. I consider containers to be tightly coupled if they work together and if they should be replicated at the same time. For instance, let's say that you have a server container and a DB container. The server is used a lot, whereas the DB is only used a little. To meet increasing demand, you'll need to replicate the server sooner than the DB. Thus, they're not really tightly coupled and should live in separate pods. Alright, enough theory. Let's talk about how you can create a pod. Here's an example of a YAML config file for a pod. The pod holds a container which prints the first 1000 prime numbers. There are 4 key sections of the config file: the API version, kind, metadata, and spec. Every component config file will have these sections, although the format of these fields will differ from one kind of object to the next. The API version defines the version of the config file schema. Honestly, I rarely think about the API version because I don't write config files from scratch very often. I just copy and modify an existing config file. Next we have the kind field. It holds a string which indicates the type of Kubernetes component that this config file defines. The metadata section holds things like the name of the component, various labels, and annotations. The name of this pod is primes, and the name of the config file is primes-pod.yaml. Note that there's no relationship between the two. They were both arbitrarily chosen by me. Next we have a label. It can be used to select the pod as the target of various operations. We'll go over labels more in the next chapter. Finally, the spec section contains all of the fields which define the desired state of the component. At any given moment, the object, i.e. the Kubernetes cluster component, may not match up with the desired state described in the spec section of the config file. After all, the config file is just the template for the object. This pod's spec only has a containers field. The containers field is an array of one or more containers which live and run in the pod. In this example, the pod has a single container named primes. Every container in a pod must have a unique name. It must be made up of no more than 63 alphanumeric characters and hyphens. The image field specifies the Docker image used to create the container. So the example pod pulls the image true Kubernetes /1000 primes with the tag 1.0 from Docker Hub. Later, I'll show you how to pull images from private registries. Now, you might be worried that you'll need to memorize the exact config file format for each different kind of Kubernetes object. Thankfully, that's not the case. When you create a new config file, you'll usually just copy another config file of the same kind. You'll then modify the copy to suit your needs. Okay, in the beginning, config files can make your eyes cross, but don't worry. You'll be able to read them at a glance with a little practice. Here's a little bit of advice. The first thing that I look at is the kind field. This lets me know what the structure of the config file will be. Then I focus on the spec section because it is always the heart of the config file. I almost never look at the API version, and I only glance at the metadata as needed.